Hey everybody, welcome to the overview of the final. So here we go. This is the summative task, and we're talking about rising tides in San Francisco here in the Bay Area. Here's the overview. You're an oceanographer. You're reporting to the City of San Francisco City Council about past and future changes in local sea level due to climate change. You're working with sea level measurements from a tidal station just north of Crissy Field, which is the oldest continually operating tidal station in the Western Hemisphere. It's been taking data since 1854. There's some pictures of the actual station. So part one is to illustrate the changes in sea level around San Francisco in the recent past. You brought a graph of mean sea levels over the last 50 years. To make long-term changes easier to see, the sea levels at high tide were averaged over the 10 years, and then the graph was smoothed with a polynomial fit. So just like in terms of understanding what this is saying, the data was made nice and easy with a polynomial fit. And going back to our big ideas packet, the polynomial fit is found all the way near the bottom where you look at important terms. And here we go. A polynomial fit is basically when you take statistical data, any data, and sometimes the data, usually in the real world, is messy, just like you see right here in these graphs. These points right here, these are the data points, and the curve right here is the polynomial fit. Polynomial fits are polynomials that represent data. Just in a smooth way. It records the trend, right? Not every single data point is going to go through it, but it predicts a good, accurate trend. A polynomial fit basically gives you a polynomial, like a function to represent the data. And not exactly will you be doing this. This is actually, it's like a polynomial fit was made for you, and you're going to try to reproduce what that polynomial might have looked like for the sea levels. But just a little bit of review on what is a polynomial. A common one y'all have worked with is probably the quadratic function. It talks about what degree it has. There's also cubic functions, quartic and quintic. The higher the degree, which is the highest exponent in the polynomial expression. For example, this is to the 7th degree. The higher the degree, the more curves and turns the graph has itself. So that's just what a polynomial is. An important thing you should know about polynomials is they're usually smooth. They're usually a smooth graph. So when you're creating your model of the sea levels, it should be a smooth graph. So that's just the main thing right there. Again, unfortunately, your laptop is broken, so you can't project your graph to the city council. Fortunately, you remember some key features of the smoothed graph. In 1970, at the start of you taking data, the mean sea level was negative 62.33 millimeters below the sensor line. All right, so we have like a recording point, sensor line. I'm thinking that might be the origin. If they're not telling us to put it anywhere else, I might make that the origin if that's the easiest way to do it. Okay, next, average rate of increase in mean sea level. Average rate instantly makes me think velocity, because I know velocity is the average rate of an object in motion, right? And we could take the average of sea level, right? The average rate of the sea level rises. We could do that. It's like finding the velocity of the mean sea levels. So we could totally do that. And again, rate time graphs such as speed or velocity, again, we could think of this as the velocity of how fast the tides are rising, or how slow they're rising, or how fast they're decreasing over time. But of course, sea levels are rising due to climate change, so we're talking about an average rate in rise. So I instantly think velocity, so we might need to use velocity formula. And again, the mean sea level average rate of increase from 1970 and 2020 was 2.35 millimeters. So I know that the average rate between 2 points is going to give me 2.33 millimeters. And again, there's going to be an additional support video to figure out how to do this bullet point. But I'm also interested to see what ideas y'all come up with. Now right here, third bullet point. So this indeed is 3 times. We double checked that. So this is accurate now. So the mean sea level has changed directions 3 times in the last 50 years. Now change in direction, super important. We talk about changing directions. We talked about it in class, like when does an object change directions with different types of graphs. Um, and let's see where we talk about change in direction. Okay. I think right here, yeah. So right here, big idea number 6. So when velocity is positive, or basically when the slope of your position graph is positive or increasing, it means the object is moving forward. And when the velocity is negative, it means the object is moving backwards, right? Whoop, right? Well, here we go. Here's the diagram, right? Forward, staying still, going back. Now, how are we going to apply this to sea levels? Very simple. So sea levels is up and down motion instead of side to side motion. So positive velocity will mean sea levels are moving upward. Negative velocity would mean the sea levels are moving downward below the center line. And of course, velocity is 0 means the sea level isn't moving much at all. So that's how you would apply it to this problem. And again, yeah, you're going to apply the change in direction in that. So also, if you look here in this here graph, change in direction from positive to negative, that means there's a change in direction happening once right here. It went from forward, stop, move backward. So a change in direction happened once. Then you're going backward, then forward, happened twice. So basically, each time you see kind of like a little max or a min in your graph, it's like a change in direction, um, according to what I'm reading right here. All right. Now, and then we have that as a result, the graph has 3 relative extrema between its endpoints, and they give us where the relative extrema are at the specific points in time. And relative extrema, if you go back to your big ideas packet, is right here. Important terms. Again, they're all, they look like the lowest or the highest point in a graph. The best way to explain this is looking at this picture right here. I call them humps or maximums, minimums. We call them relative because locally they're a relative maximum or relatively a local minimum compared to its local location, but that's what they are. High points or low points, basically. So that's what your graph should have when you recreate the model. So based on these facts, you're going to recreate your graph of mean sea levels between 1970 and 2020 as a sketch. And time should be x-axis and mean sea level should be the y-axis. This right here gives me a lot of information. That gives me a place to start, with an x and y-axis and how to label them and so forth. So that's a great way to get started on this part. All right, for part 2, Part 2 says, so part 2 is not supposed to be related to part 1. It is kind of related, but the data is different for part 2. That's just a heads up. So one of the city council members responds that you said you're using smooth data for this graph, but I don't believe that's appropriate. Here I have a graph of smooth data in red. See, that's the polynomial fit in red. But I don't believe it's appropriate. I have here a graph of smoothed I have here a graph that's smoothed in red and unsmoothed blue mean sea levels for the last 30 years. So notice how in blue it's different, right? The actual data points are different from the polynomial fit. So the two are totally different, he says. The red curve only changes directions 3 times, but the blue curve changes directions, look at this, dozens of times because there's lots of high and low points. So therefore it changes many more times than 1, 2, 3 points. So then the councilman says, therefore, the two graphs must disagree on the average rate of sea levels increase over this period. And your job is, do you agree or disagree with the council member's argument? Support your conclusion by explaining how average rates are calculated. Again, average rate, think velocity if you go back to your big ideas packet. Okay, so sea levels, so for part 3, this is about acceleration. And again, going back to your big ideas packet, you're going to find where we talk about acceleration and use what you can about, so if you have a velocity graph, how to determine acceleration. I think this is what we have on acceleration right here. You can see if we have any other things about it, but this is what I found, big idea number 7. So the sea levels, by the way, y'all, are are not only rising, but they're accelerating. That means they're speeding up. This acceleration has severe consequences for our predictions of sea levels toward the end of this century. So the graph below shows projected rates of sea level rise near San Francisco under two models. The one in blue is when we have a model that accelerates, and the one in red where the sea level remains constant. Now, whenever you're looking at a graph with data, always look at what the y-axis, x-axis are giving you, because like, what am I looking at first? Is this position? Is this velocity? Is this acceleration? So look here. So this right here is millimeters per year. So this right here, I know it's a rate. And the rate that I'm going to interpret this is like a velocity graph because it's millimeters per year. That's a rate. I'm going to say that's the velocity of the sea level rise. And over here is our time. So what I'm looking at is a rate time graph. And again, that was like our major opening big idea, number one. And you all can go ahead and read through this, but we talk about that. And your job is to estimate the projected total increase of sea level from 2015 to 2075 under first the model without acceleration, the one in red, and then one with the model with acceleration in blue. So that's basically the overview of it, and the City Council wants to know why they should care which model is more likely to be correct. Explain why the difference between two models is significant based on the calculations you made in the previous part. So there we go, y'all. Like I said, I'm going to be making another video that helps y'all get started on part one. But I definitely think y'all can get started with a model that has all of these qualities and so forth. And I'm excited to see what work y'all produce. All right.